nanoHUB.org.
Online simulation and more for nanotechnology.
Sayan is a postdoctoral research assistant in the School of Electrical and Computer Engineering at Purdue University. He obtained his bachelor's degree in 2013, master's degree in 2017, and PhD degree in 2021, all in electrical and computer engineering, ECE, from Purdue University. His current research interests includes transitional metal dichalcogenides, TMDCs, photovoltaics, photonics, and nanoelectronics. His doctoral research topic was modeling of ultra-thin 2D TMDCs for nanoelectronic and photovoltaic applications and implementing advanced techniques with a focus on tungsten disulfide, tungsten diselenide, and hybrid tungsten-based TMDCs. His postdoctoral research topic is investigation of 2D materials and TMDCs for quantum applications and radiation-resistant electronics. In addition to his research activities, he has been a teaching assistant and instructor for several courses in the ECE at Purdue University. Thank you so much for joining us today, Sayan.
Thanks for the introduction. Hi, everyone. Good morning, good afternoon, or good evening from wherever you're located. Thanks for joining in. Thanks for the great introduction. I think you already know what I have been doing and what I do right now. So I'll talk about how we can model pn-junction devices for photovoltaic applications. Okay, so basically, you know that solar cells are simply large area pn-junction devices. So where you have incident photons from the solar radiation, and which creates electron-hole pairs. And then if we can collect the electron-hole pairs in a efficient manner, we get current. Okay, so this is a very simple illustration of solar cell architecture. Okay, so we have typically can have an N-type layer, a depletion layer, and a P-type layer. So the depletion layer is from simple semiconductors physics. So where you have the junction of an N-type layer and P-type layer. And once photons are incident, you have electrons and holes which are generated. And if we have design a mechanism where they flow to the opposite sides of this structure, we can get current in the external circuit. Okay, so the concept is very simple, but it's important to understand what are the different parameters and conditions which are needed to simulate a solar cell. Okay, so solar cells can be simulated using the tool ADEPT, which I'll be mostly talking about today, to obtain the current voltage characteristics, the band diagrams, the external quantum efficiency, and also the performance parameters such as open circuit voltage and short circuit current of solar cells. Okay, so I'll briefly talk about ADEPT, and also I'll talk about how to get some of the properties, and then I'll change from the presentation mode to go back to the tools on nanoHUB and look at some sample demonstrations. Okay, so ADEPT. So what is ADEPT? So ADEPT stands for a device emulation program and tool. So this program solves the semiconductor Poisson's equation and the hole and electron continuity and transport equations, assuming drift diffusion transport, subject to appropriate material parameters. So it solves the semiconductor equations, but then you have to know exactly how to define your materials, and what other parameters are input to the system. So ADEPT can be used to model simple single material solar cells, such as silicon-based solar cells, gallium arsenide solar cells. It can also be used to model thin film solar cells like cadmium telluride or CIGS, which stands for copper, indium, gallium selenide. And you can also use it to simulate multi-junction solar cells. Okay, so now the input part of ADEPT. So if you want to run ADEPT successfully, you have to make sure that all the input parameters and the control files are very accurate, and we don't overestimate a particular parameter, or we don't underestimate anything, or we don't put in something which is total some garbage value or something which doesn't make sense. So I'll break down the input file into three major aspects. So first is the device parameters. Okay, so what do we mean by device parameters? Is simply that we have to be able to define the exact solar cell device very accurately in terms of the number of layers, the boundary conditions, in terms of the contacts, and if there are any additional features like back surface reflection, if you have any top additional absorber layers, or anything which can affect the performance from a device level perspective. Okay, so I'll go into the details of the parameters when I look into the tool. Okay, and then the next is the material properties. So let's say we are working with a simple two-layer device. Okay, so we need to define the properties of the individual layers very accurately. Some of the most important parameters which have to be defined very accurately is the band gap, the absorption profile. Okay, so the band gap basically tells you like which photons will be absorbed. The absorption profile basically tells you the photons of different energies which are absorbed, and also by what extent. Okay, so this is vitally important for any solar cell operation. Like we need to understand how the device behaves when a particular spectrum of the solar radiation is incident on it. Okay, and then you have additional parameters like carrier mobilities and lifetimes. Now there are a lot of parameters which are needed. I wanted to mostly focus on carrier mobilities and lifetimes is because these two parameters affect the output current by a large extent. Now very simply, why are they important? Let's say you have a large area solar cell and you want to model it. Right now, if you're modeling it, you're kind of modeling an ideal device. Okay, so we don't take into account any defects or any non-idealities or any structural deformations in the layers. But when you're working with an actual physical solar cell, they can have a lot of lattice defects, structural deformations, although they're usually very low in number, but they're usually non-zero. So one way to work with those non-idealities is to have very conservative estimates of the carrier mobilities and lifetimes when you're modeling it. Like when you're modeling it, you can basically put in any number and get the theoretically highest possible device performance. Okay, but that's not always the goal, right? Because we want to model something which kind of resembles the experimental results, or which have been demonstrated experimentally in some other devices. Okay, so these two parameters are very important to kind of limit the ideal assumptions and take into account non-idealities. Okay, and then finally, the other important aspect is the operating conditions. So the most important part of the operating conditions is the solar spectrum. We have to know what kind of spectrum which we are working with. Typically, for most solar cells, we are working with the terrestrial solar spectrum, which is simply the AM 1.5G solar spectrum. But this tool is set up so that you can use pretty much any spectrum. Like you can use a custom spectrum file. Okay, like if you only want to focus on a part of the solar spectrum, or if you want to look at, say, space photovoltaic applications, so that would correspond to the AM0 spectrum file, right? So you can also use the AM0 spectrum file as the input to the program to run a simulation of the solar cell in the space environment. Okay, now if you run it for a space environment, there are a lot of other issues which come into account. So I won't go into too much details about that, but then the major takeaway is that you can define any spectrum file which you want to run the simulation. Okay, and also you can define the temperature. So this typically works for most temperature ranges on Earth. If you go what I've seen is if you go to really high temperature values, about say 100 degrees C or 120 degrees C, then like the lot of inaccuracies come into play. And also the other issue is like even your material might not be very stable, and there might be other material-based issues which cannot be modeled in this tool. So although you can enter the temperature, but typically it's most accurate if you have temperatures within the range of what you encounter on the surface of the Earth. Okay, so this is what ADEPT does mostly. This is the link where you can, it's freely available. You can create an account on nanoHUB and access the tool. Okay, now it's very important to understand, okay, where the optical and electronic properties come from. Okay, so when you're defining the materials and when you're kind of looking at the band gap, density of states, the absorption profile, we need these properties beforehand before running ADEPT. ADEPT cannot calculate these parameters. So ADEPT is just simulating the device you enter and the environment. Okay, so I'll briefly talk about a couple of ways and a couple of tools. So one tool is mostly for electronic properties, and the other tool is mostly for optical features. So density functional theory, or DFT, it's a quantum mechanical modeling method. It can be used to investigate the electronic structure of many body systems, in particular atoms and molecules. DFT calculations can be carried out using the open source code Quantum ESPRESSO. So DFT is very useful for calculating properties such as the band structure, band gap, density of states, absorption coefficient, etc. of any photovoltaic material. Okay, now nanoHUB has a version of Quantum ESPRESSO which is in this link over here. You can have a look at it to see how some of the properties such as the band structure, band gap, density of states are calculated. Okay, but I do want to mention that DFT and working with Quantum ESPRESSO can be its own project in its own right. So DFT is not something very straightforward. Typically, what I would say is if you're working with some known materials and if you want to look at the photovoltaic behavior, it's best to see that if you can already find some of the parameters such as the absorption profile and the band gap from existing sources. So if they're typically known materials like say silicon, gallium arsenide, or aluminum gallium arsenide, so for known materials, the properties already out there. So it's kind of not very helpful to do a full DFT calculation to get all the properties. But it is vitally important if you're working with some unknown materials. For example, for my PhD, I worked on transition metal dichalcogenides, or TMDCs. I mostly focused on tungsten disulfide, or WS2, and there wasn't much resource out there on WS2. So my first project as a doctoral student was basically running a DFT calculation with the WS2 material and to simply get the fundamental properties even before we can work on ADEPT. Okay, so if you're working with some new materials, you can use DFT, you can use Quantum ESPRESSO to get the properties. And next, so another aspect when working with solar cells is we might have additional optical layers. They don't have any electronic function, such as a window layer on top, which can basically act as an anti-reflection coating. Okay, or you can have a light trapping grating, which basically increases the optical path length in ultra-thin structure, so you have additional absorption. So there's another tool, it's called Stanford Stratified Structure Solver. So this tool was developed by a group in Stanford, and this tool is also available on nanoHUB. So this can be used to simulate the absorption properties of multi-layered structures, including pattern layers. So S4 is a frequency domain code to solve layered periodic structures using rigorous coupled wave analysis, or RCWA, and the S matrix algorithm. And this is the tool for the S4 tool. So now again, it's important to keep in mind that the fundamental absorption properties, okay, cannot be calculated by S4. So if you're looking for the baseline epsilon function or the absorption coefficient, you need to perform DFT calculations with Quantum ESPRESSO or any other tool. But then if you want to see the behavior of the absorption profile in different configurations, such as if you have an anti-reflection coating, if you have a light trapping grating, okay, so then S4 becomes very useful. Okay, so these two kind of work hand in hand with each other. So I've used all these three tools in my projects. Okay, so and then I'll briefly talk about S4 and how we can use it to understand absorption and reflection. Okay, so that's the last slide. Then I'll go to the tool and show exactly how we can perform some sample simulations. So this is the tool ADEPT. Okay, and so I've kind of logged in and I've started the tool. So this is the first page which you get when you run ADEPT. So, and there are some a few pre-built example structures given over here, okay, which you can run just to get the feel of it. Okay, and I'll briefly go over the inputs and some outputs and just show you what we can do with it. Okay, so remember I mentioned that you have to be careful in defining the material properties, the device parameters, and operating conditions. Okay, so the first step is just defining the number of layers. Okay, so you can define the number of layers, and that gives you 3 tabs, and you can define the individual materials in each layer, okay, to kind of model the device. So some of the important properties are shown here. So you basically have to input the parameters, all these parameters which are given over here, but I'll cover some of the fundamental ones, such as the layer thickness, and typically we use doped materials, so you can have a doping type and a doping density. Okay, and then the band gap is vitally important. Also, the electron affinity, the dielectric constant, the conduction band effective density of states, the valence band effective density of states, the electron mobility, hole mobility. Okay, so these are all material-based properties. And most of these are kind of available for known materials. There are a lot of resources out there, but if it's a new material, you can do DFT calculations on Quantum ESPRESSO to get most of these properties. Okay, and then also there are the values of electron mobility, hole mobility, and you have the various lifetime parameters. So typically you can see that you can pretty much enter any value you want, and then you still get some output, but it's a wise idea to use conservative estimates of all these lifetimes to get results which kind of match experiments. Like, we don't want to overshoot what can be achieved experimentally. Okay, so we have it's a 3-layered device, so we have the 3 layers, so it's important to define the individual layers very accurately. Okay, now next, again, another vitally important parameter is looking at the absorption profile. Okay, so on the absorption tab, we basically have to enter the absorption coefficient of the materials for different wavelengths. So this is wavelength, and alpha is the absorption coefficient. So there's a supporting document file under ADEPT, which basically tells you the format of the absorption coefficient file and what the columns mean. So I'm not going into too much detail since it's already out there. Okay, but the absorption coefficient again is vitally important. We have to be very accurate in this part. So Again, quantum espresso can be used. Like we can use DFT calculations to find the absorption coefficient of the materials. But then if it's a known material, you probably have a lot of resources out there with the absorption coefficients, and then we can use it directly. Okay, so basically each layer needs a absorption coefficient. And then if you go to the global tab, so these are mostly computing parameters. So you can choose the front contact, the boundaries, and the key thing to keep in mind over here is the temperature. So you can change the temperature. Like I'm not going to detail too much detail. Okay, so but the temperature is the most important aspect. So just to give you an example, like you can use 300K, this is Kelvin for most terrestrial applications, but I've used one of my projects for space photovoltaics, and then we needed temperatures of around 320, 330K. So we really can't use room temperature. So you can play around with the temperature range a little bit. Okay, and then finally, if you go under the simulation tab, again, the most important aspect is choosing the spectrum file. So most of us will be using the M1.5G spectrum, since that's the terrestrial solar radiation on Earth. Okay, and you can have additional parameters such as if you want a back surface reflection, if you want to multiply the illumination intensity, or if you want shadowing, and some other parameters also. Okay, so now if we just so we have set the operating conditions in terms of the spectrum and the temperature. We have the device parameters in terms of defining the device, and we have again the individual material properties. So if we just click simulate, okay, so now I already ran the simulation previously, so you don't have to wait. Typically it takes a few minutes. So once you run the simulation, you get a bunch of outputs. Now, the most important output would be the IV characteristic. If you were to look at solar cells, so you can see this is the short circuit current, which is around 39 milliamps per centimeter square, and this is the open circuit voltage, which is around 0.6 volts. Okay, and now there are a lot of other outputs which you can get. You can get the energy band diagram and see how the energy band diagram looks. And you can also get the quantum efficiency, but then it does not give the quantum efficiency in the single run. You basically have to run it a separate simulation which specifically calculates the quantum efficiency. Okay, and if you look at the output log, okay, like that basically gives you all the parameters which you need in terms of the device operation. Like the output log has the VOC, it has the JSC, it has the fill factor, and it also gives you the efficiency. Okay, so you can get all the parameters. Okay, now I want to move on and show some other simulations. So I'll briefly talk about another simulation using ADEPT. So this is a different simulation. So this is one of the materials which I work with. So this is a 3-layer device, but it's not silicon. So it has tungsten disulfide and it has like amorphous silicon. So the 3 layers which I have defined. So this is thin layer of monolayer tungsten disulfide. This layer 2 is bulk tungsten disulfide. This has all the parameters of tungsten disulfide. And then this is amorphous silicon. Okay, so this is the 3-layer device structure. So I have the absorption profile of the individual layers. Like this is monolayer tungsten disulfide. This is bilayer tungsten, bulk tungsten disulfide, sorry, not bilayer. And this is finally amorphous silicon. Okay, and then I'm just using the 1.5G spectrum. And then again, if you run it, so this will give the output for this device. So we can get the IV characteristic, so this IV plot, and also we can check the output file for the exact parameters. So it's typically somewhere in the middle of the output file. Yes, so this tells you what the VOC is, what the JSC is, and also fill factor and efficiency. So I have so this is directly from one of my research projects. So I modeled this solar cell, but then also I had to get the individual material properties using DFT. Okay, so I think so that's what I mostly want to talk about for ADEPT. So you can use ADEPT for pretty much any material or device configuration as long as you define the device or material parameters very accurately. So if the fundamental parameters such as the band structure, the band gap, density of states, and like the absorption coefficient are incorrect, you will get totally incorrect results. Okay. Now, finally, I want to briefly talk about two other tools. So one is the tool S4. Okay, so S4 stands for the Stanford Stratified Structure Solver. So what this basically does is that if you know the material parameters, like specifically most important parameter which you're dealing with over here is the absorption coefficient or the epsilon function. If you know the epsilon function of a material, you can create a layered structure, a pattern layer with different gratings which can assist in light trapping or other optical phenomena to get enhanced absorption. For example, this is just an example which is pre-built over here. Okay, so this is just a simple binary grating using aluminum gallium arsenide material. Okay, so you can also define your own material. So I'll just run the simulation and show you what it gives us. So again, it takes a few minutes. I ran this previously so that we don't have to wait during this talk. So this basically gives you these two curves. So the blue one is simply the incident flux, it's just unity. So the green one is the transmission flux, which basically tells you the spectrum which is transmitted, and the red one is the reflection flux, which is reflected from the material. So and then if you just take the incident flux minus the transmission flux minus the reflection flux, you basically get the flux which is absorbed in the material. Okay, so this way you can just test this your material to see what the absorption profile is for a pure material. So for a pure material, the absorption profile will be very similar to the absorption coefficients which you calculated using DFT. Okay, but if you put in some patterns, like this is a binary grating, okay, then it's really a nice tool to understand how the gratings or the optical features your kind of define or modify absorption. So I'll quickly show you the control file. Okay, so there are two sets of inputs which are required. So for each material, so we have only one material in vacuum, we need the values of the epsilon function. So again, if you have it from known sources, it's very good, but if it's a new material, you have to calculate it using DFT. So we need the epsilon function. Okay, and then we have to see when we add the layers. So these functions basically add the layers, and we can set patterns. So this command simply sets a layer pattern, a rectangular pattern in the material. So we can set different patterns. We can have circular gratings, we can have triangular gratings, we can have a lot of different patterns to kind of simulate any optical features in the materials. Okay, so I think we're almost out of time. So I'll just very quickly talk about the DFT simulations on using Quantum ESPRESSO. Okay, so this is the Quantum ESPRESSO tool on nanoHUB. Okay, so which you can do for DFT calculations. So this has some pre-made examples, like it has silicon, it has tungsten disulfide, which I work with, it has molybdenum disulfide. Okay, so let's say I want to simulate tungsten disulfide, for example. Okay, so you have to define the structure type, so the unit cell, and then this basically defines the unit cell in terms of the number of atoms and the location of the atoms, and also this you have the lattice parameters. Okay, So I'm not going into too much detail since DFT by itself can be its own talk. So there's a lot of aspects, but you can look into this tool to just kind of get a feel of what DFT is. And if you just simply simulate this, okay, it should be very fast. So you can get a density of states. Okay, and okay, like it's not a very accurate. It's fairly accurate, but it's not a very nice plot since we are only using a few points for a faster calculation. So you can see that you have no states within this range. So this basically corresponds to the band gap of the material. You can get the electronic band structure. So DFT, what it does is it basically gives out whatever you put in. So you cannot expect the exact textbook like band structure for DFT. So you kind of have to know where your valence band and your conduction bands are and work with it accordingly. So this is the band structure. It gives out all the bands which are present, but then you have to know where to look into. So if you zoom into this part right here, you can see this band structure kind of behaves more like what you have seen in a textbook. So this is typically the valence band, this is the conduction band, and so you can get an idea of what the band gap is and all the other parameters. Okay, so you can see it has, you can look at the input files and output files to see how they work. But then again, I want to mention that if you want to do a full DFT calculation with the absorption coefficient, and if you're looking some hybrid materials, you kind of need your own access to a computing cluster and the Quantum ESPRESSO installed on your own machine, since just because of computing resources or the lack of enough computing resources, this tool cannot do all the calculations which are needed for proper material modeling. So you can look into it to kind of just get started and understand how DFT works. But if you want to actually get results for research problems and publications, you need to get your own version of Quantum ESPRESSO and get access to a computing cluster. So yeah, thank you for your attention. Hope it was helpful, and I think there are a lot of questions, so I'll try to get to the questions on the website and answer them as soon as possible. Okay, yeah, thank you. Thanks for your time.
Sayan, thank you so much for your talk today. It was wonderful.
Thank you very much. Thanks for having me.